to close this app, because I'll move on. So to close this app with VQE, QAOA, basically I wanted to kind of give an overview on the differences of two, if I can find anyhow that difference, because it's still a bit blurry to me. But basically, I still believe there's a mistake in here, although I don't fully. Because if you take a look at the ansatz, right? So the parameterized one. So you've got x rotations, z rotations, control z's, and then control z's with x gates in the front and in the back, and then you've got measurement, and that's about it. But it's all so it's all uh, z related operations. So it's when you try this something like that in Quirk, you can see that the only thing that basically affects the final measurement probabilities is really the first layer, which is really confusing. And then to add more on top of this confusion, I've been doing some browsing here and there, because I remember back when I was starting with the Yellow Submarine project from Mihao, came across a paper that was an introduction. It was not the actual QAOA paper, but it was sort of an introduction to QAOA. Is this one? No. I think it's this one. No, that's the actual paper from Fari and Jeffrey. I think this is the actual original paper. I think. Damn, that's pretty recent, 2014. It's called Introduction to QAOA, something like that. Yeah, I think it's this paper. Because here they basically discuss the maxcut problem, and then they also, I realize now that they do the traverse Ising model as well. This kind of, I did a bunch of videos on this paper, I think, and I don't know if I think I got those papers totally wrong, because I'm not so sure whether I was doing this correctly, as in, like, I was literally, I think, in those papers using that circuit when this is obviously not for the max cut, I think. Anyway, but what is it? Is it the max cut? It's just this? I don't know. So he is a sort of a. It caught my attention, because if you pay attention, there is the. I don't know if you're gonna see the zoom, probably, hopefully. So there is the Hamiltonian here, but there is a bit of a difference between these and what the Circ paper, the Circ tutorial mentions, which is basically they put all those components in the Z, like they all. I'm not so sure exactly what this means mathematically, that you put the Z in here, but that then translates into Z gates, right? And here, here you've got is it sigma? I think this is Z, and then X. So these two denote the interaction between adjacent spins with strength J blah, and then H sub J denotes the external magnetic field. He would consider J to be 1 and H1 to be 1 always. Okay. In addition, we have boundary conditions so that the last term in the first summation is N1. Okay. So this is even then looping. Just closing the loop in this case. We can implement this in QAOA with C equals H. Then they go with a bunch of notation in here. And so they basically and they basically come up with this circuit where it's pretty similar, but here you've got. If it's not clear to me what's the starting state, and here you've got control nuts and then Z rotations. So it's kind of a bit different. But then they also mention here that you've got to process the results, you've got two parts, H1 and H2. One is this part over here, another one is this part over here, I understand. Don't get it though. They seem to be the same. This seems to be absolutely the same. I don't get it, because it should be these, maybe. I mean, so at the final state, so the first term on the right can be calculated directly based on the distribution of Z bases, since final state is an eigenstate of Z matrices. I mean, yeah, so basically what this is saying is, because Z is our computational basis, and that's from that perspective, then you just measure the results and go on with it. But the second term requires more work, since phi is not an eigenstate of the Pauli X matrices. In order to get the second term, we have to measure the result with a change of basis from Z to X, applying Hadamard gates with the measurement. So they do apply Hadamard gates in here. I don't know. What I will do is I think I will post a question in I'll post a question after this video in the quantum computing Stack Exchange, and see if anyone can give me an answer. Maybe I'll contact the, I don't know if there's a way to contact here and ask. It's not that I it's not that I think it's a mistake, but it's just I mean, you obviously get, you know, different results, because it's, I mean, those are quantum runs, right? So you're gonna get always different results. That's the randomness in it, but there's no change. Obviously, if I go in Quirk and I just and I do, like, you know, as we were doing. So we'll just do a smaller example with 3, and we'll just do, like, I don't know. So what was that? What were the values used in here first? It was 0.1, 0.3, and 0.7. Okay. So this will be 0.1. This will be 0.1. This will be 0.1, and then there was a Z. I don't know. I'll just you know, Z will be 0.3, and then I will make give me a second. Sorry, I had to pause for a second. But okay, so and then it was like, I don't know, control. It was a control Z, so control. Let's do this, and then let's do 0.7. My point is, just doesn't matter. You can make that example bigger. You can make more of those things. I can make, maybe even do the other one, which is 0.7, and then also have these things here, right? So my point is that if I put an amplitude here, an amplitude display here, it's from a and a chance display here, from not a chance display, but a chance display, like this. I mean, you can also have this one here. As you can see, it's absolutely the same after the X rotations. The only thing that changes, obviously, are the phases. But as we are just measuring, as we're just measuring, just directly measuring, then there's no no point in this. So I don't know. I'll put a question. I'll probably even share this, use that example. But basically, that's kind of a weird thing. And then there's a bit of a discrepancy here in terms of, I know this doesn't seem to be the same, or n aligned one-dimensionally interacting spin chain, because the Google says two-dimensional, but the Hamiltonian seems to be the same. So I don't know. Yeah, whatever. So basically, this is. I'll put that, and then as soon as I get an answer, I'll probably make another video on this, because I'm at the moment I'm kind of lost. So maybe I'll just I'll come across a solution later. So I just wanted to move along, and then basically talk a bit QAOA and VQE in general, and then the next video I'll do will be. Well, I will basically come back to the yellow submarine project. I'll come back to the continuous variable quantum computing just for a brief period of time, maybe 1 or 2 videos. Actually, I can probably show you my Trello board on these guys, because I've basically been cleaning some of these things up in here. So I'm trying to focus on this part in here, this part in here. So I want to basically close those things. Then I was thinking about doing HHL, PCA, SVM, so principal component analysis, support vector machines, because this is kind of the part from the O'Reilly book that I really didn't do, but I also know that they are in this paper, Quantum Algorithm Foundations for Beginners, which I also wanted to take a look at. So we'll see. I don't know. There's a bunch of other stuff that I want to work on here as well. Now that Microsoft has released also is putting their stuff, like is putting ion trap quantum computers on the cloud. Want to learn a little bit more about it, and then yeah, just going ahead with different papers and other things. There's some interesting stuff from Alira that I wanted to read as well. We'll see. I don't know. So far, this is what I'm trying to do. Yeah, cool. So now that you know this, let's just do a quick search, because this is definitely one thing, right? So it's like I don't know how else could I try to prove. It keeps bothering me. I can't move. I can't just leave it like that. I don't know. It doesn't. Almost didn't sleep tonight. So what if I just Google QAOA versus VQE? Because I even don't remember. Blue cat. Oh, so here we go. Is VQE a class of algorithms or a specific algorithm? Is VQE a class of algorithms or a specific algorithm? For example, QAOA is QAOA a VQE or VQE an algorithm distinct from QAOA that solves the same class of problems? Because specific algorithm, what is the defining features? Okay, so okay, let's see. I view QAOA as an algorithm for solving approximately a special class of problems, namely combinatorial problems. Combinatorial problems. VQE as a possible subroutine to QAOA. Ah, it's an interesting way to see this. Okay, but not necessarily as in the case of MaxCat. Okay, the VQE solves the problem of approximating the smallest eigenvalue of some Hermitian operator H, which we usually just call Hamiltonian. As a byproduct, we also obtain a classical description of the approximate ground state. It does so by classically varying over efficiently preparable ansatz states, and a quantum subroutine determines the expectation value. By a sampling procedure. Okay. In QAOA, quantum approximate optimization algorithm, your cost function, or Hamiltonian if you will, is given by these. Okay. Where the Ci Z are operators diagonal in the computational basis. In importantly, the eigenbasis of H is thus the computational basis, and one of the computational eigenstates encodes what? This is not the case in VQE. So how does QAOA proceed? On a high level, without going into too many details, it proceeds very similar to VQE. Optimize over variational parameters in some ansatz state. The state is called this. And it ought to maximize the expectation value. Yes, it's basically the same concept. Okay, so in this step you can use VQE as a subroutine. This is precisely the task a VQE can achieve, finding good parameters, but it might not be necessary. In the original QAOA paper, the authors argued that for particular instances of maxcat, an efficient classical optimization method exists, that is, they could optimize over the ansatz state without ever preparing it. Okay. Here we necessarily go quantum in the second step. Prepare the optimized ansatz state over and over again and measure it in the computational basis until you statistically converged enough to be able to pick the right computational basis state encoding the solution with high probability. Note that because of the previous optimization routine, the state should have a large overlap with the eigenstate to the smallest eigenvalue, which I stress once again is one of the basis vectors of the computational basis. Yeah, but I thought that was the whole point of VQE. I mean, note that QAOA is just one possible application of VQE, okay? And there are many more. First and foremost, quantum chemistry problems. So QAOA is one specific case of VQ. Yeah, but then that seems contradictory to what you're saying at the beginning here. That it's an algorithm for solving. So you're saying VQE as a possible subroutine to QAOA. But basically this is not, it's just QA is a possible application of, yeah, okay, VQE. Okay. Okay, so QAOA is designed to approach combinatorial problems. VQE is more generic in the sense that, you can use it for things like we just did with the Ising model, but QAOA it's specifically designed for combinatorial problems. Now, I wanted to quickly try to understand that, because it's been really a path. I've never really fully closed any videos on QAOA because I started with the yellow. Let me show you. I started with the yellow. That's fine. I started with the yellow submarine project that opened up the box of Xanadu and maybe let me just open up Studio and I'll go to the playlists. And I'll show you because I think if I go to the yellow submarine playlist, you can see this is really in the right order, where it's like, oh, what the hell is this? And Xanadu, what the fuck? And then there's some things here, and then I was playing with quantum teleportation, Xanadu versus IBM-Q. And then here I get into QAOA, because that's basically what the yellow submarine does, is QAOA, but with quantum variational, with continuous variable quantum computing. And so I was trying to understand QAOA, QAOA is not yet clear. Then the intro paper overview, then I was implementing this in Quark, then I was testing this in Quark, and then I kind of stepped into, okay, let's now go back to QAOA using CV, but then I kind of stopped first. I stopped here because that was really hard. And I just moved on, and then at some point I came across VQE, and then I started digging into this, and it ends up being the same. Okay, so they're really closely related. So now now this makes more sense. Where was I here? So I was just, one thing that I didn't fully understand was that in QAOA your cost function is given, right? Is given by a specific, okay, so operates diagonal into computational basis. Operates diagonal into computational basis. Importantly, the eigenbasis of H is thus the computational basis. Okay. I'm not so sure I understand how this helps you solve the combinatorial problems, but maybe. So this is the actual paper. Let's see. We introduce a quantum algorithm that produces approximate solutions for combinatorial optimization problems. Now, the algorithm depends on an integer p, and the quality of the approximation improves as p increased. The quantum circuit that implements the algorithm consists of unitary gates whose locality is at most the locality of the objective function whose optimum is sought. The depth of the circuit grows linearly with p times, at worst, the number of constraints. P times, at worst, the number of constraints. If p is fixed, that is independent of the input size, the algorithm makes use of efficient classical pair processing. If p grows with the input size, different strategies proposed. We studied the algorithm as applied to max-cut on regular graphs and analyze its performance on 2 regular and 3 regular graphs for fixed p. For example, p equals 1. On 3 regular graphs, the quantum algorithm always finds a cut that is at least 0.69 times the size of the optimal cut. Okay, but what's the gist of how is this designed to solve combinatorial problems? Let's see if there's any way that I can scan through this quickly. Concentration, the ring of disagrees, max cut and 3 regular graphs. Relation to the quantum adiabatic algorithm. So, problem specified by n bits and n clauses. Each clause is constrained to some set bits. So combinatorial optimization problems are specified by n bits and m clauses. Each clause is a constraint on a subset of the bits, which is satisfied for certain assignments of those bits and unsatisfied for the other assignments. The objective function defined on n bit strings is the number of satisfied clauses, where z is the bit string and c sub alpha z equals 1 if z satisfies the clause alpha and 0 otherwise. Okay. Typically, C sub alpha depends on only a few of the n qubits. Satisfiability asks if there is a string that satisfies every clause. Yeah. Maxsat asks for a string that maximizes the objective function. Approximate optimization asks for a string z for which Cz is close to the maximum. Okay. In this paper we present a general quantum algorithm for approximate optimization. So I guess the whole point of this is basically you take your constraints and you make a circuit that is, so you map them into a circuit, right? And then you basically and then you probably yeah. So actually this is VQE, right? That's just one particular application. I mean, I think that's what you do, right? So you're putting your constraints in a circuit, and then you're probably, I don't know, what you would get into a super position and then run this through. I don't know. The quantum computer works on a 2 to the power of n dimensional Hilbert space with computational basis vectors Z, and we view one as an operator. Exactly, we view one as this figure as an operator which is diagonal in the computational basis. Define a unitary operator which depends on an angle. All all of the terms in this product commute because they are diagonal in the competition. This I don't fully understand. What does it mean that it's diagonal to the computational basis? I've come across that. I came across the term diagonal to the computational basis in my reading recently. I'm not entirely sure what this term means. I know that a diagonal matrix is one with only 0 elements on the diagonal, non-zero elements in the diagonal, and I know the computational basis is this. I'm not sure how these terms relate to one another. A particular gate could be said to be diagonal to the computational basis. Man, the quantum computing stack exchange is awesome. Matrix just encodes linear operations that transform basis vectors to some other vectors. For example, matrix M can transform vector 0 to vector, M11, M12, etc., and vector 1 into this. In this case, the matrix is written like that, and vectors 0 and 1 are encoded as this respectively. In a different basis, the same linear operation has different matrix encoding. Diagonality is not preserved under basis change. Yeah. How does that answer your question? Diagonal to the computational basis. Okay, meaning that it is expressed in that computational basis. That's what it's mean. That's what it means. I think it's just, why wouldn't it be? That's does this have to do with the fact that here here's exactly what they're saying is that as the reason of you having to apply the Hadamard gates in here. I think so. This result suggests a way to design an algorithm, pick a P and start with a set of angles that somehow make FP as large as possible. FP being the expectation value, okay, and C being, in this case, yeah, C being, in this case, your set of constraints. Yeah. So maybe that's what these guys mean here by. Was it here? No, they say they'll take a QAOA. Okay, no, they just mentioned QA strategy to building the ansatz. So. Where am I? Fixed P algorithm. Commute through and cancel out. So the operator in equation only involves the edge jk and edges adjacent to jk and qubits in those edges for any p. We see that the operator in routine only involves edges at most p steps. Oh, sorry, we already. So okay, so we're already in the max cut. So we now explain how, for fixed p, we can do classical purposes and determine the angles that maximize. This approach will work more generally by illustrated for a specific problem, max cut. For graphs with bounded degree, the input is the graph with n vertices and a set of edges, string Z that makes. Okay, yeah, but then they go into these. I've already gone through these with the videos. Yeah, but then that's just there's no actual circuit here to take a look at, right? That would be too good. Quantum adiabatic algorithm. Mm. Large, but the QAOA works by placing a state with a large overlap with the optimal string in distance. Symmetric in the a variant of the algorithm. Conclusion. The input is an n-bit instance. The input is an n-bit instance with an n-bit instance of your problem. So that's the input. Okay, with an objective function c that is the sum of m local terms. The goal is to find a string z. Okay. In the basic algorithm, each call to the quantum computer uses a set of 2p angles and produces like a particular state, as followed by a measurement in the computational basis yielding a string z with an associated value. Exactly. Repeated calls to quantum computer will yield a good estimate. Yeah, that's what we've been learning now about VQE all the time, right? That's just one particular example. Running the algorithm requires a strategy for picking a sequence of sets of angles with the goal of making FP as big as possible. So we give several possible strategies. In section 2 we focus on fixed P. Because repeated calls. The QAOA can be run on a quantum computer with P growing. Still not completely clear if there is a particular strategy to build a circuit, or it's it's just like figured it out, right? You've got a set of constraints, and how do you map them to a circuit is your thing. Let me see if there's any. Define angle dependent quantum state. Because then there's this introduction paper here. Where they go through the actual example. Yeah, I think that is basically problem dependent how you build that, right? But that's the idea. It's interesting how different objective functions C apply to QAOA. Different C means different set of clauses. The max cap problem as an example can be phrased this way. Suppose we have connected we can classify each vertex into different categories. Okay. So here we've got CJK equals to these, and it's 1 if the edge is a cat. It's -1, sorry, and it's not a cat, it's a 1. Yeah, and here's the way they propose a way to translate that. So I think that's it. I mean, I'll probably revisit that anyway in some weeks, because I should keep doing that anyway. Consider n vertices qubits in regard to classification of vertices assigning the state of a qubit 0 or 1. Then so product given the classification of qubits in this way. You want to use a classical objective function, so when you consider C as operator. Yeah. I mean, this I went through, I remember. So let's obtain in here. So the second layer is that only is that only some of the edges in JK need to be evaluated. In this case, yeah, I'm just running out of time for today anyway. But basically, can make more from this. The model was historical model, which is one of the most widely used multi-point simulation. It originates in the spin-spin interaction from. So the concept here is this. Basically, intuitively, you've got a set of constraints. So you've got your Hamiltonian or whatever, right? But you build a circuit, you map that into a circuit, and then you give it a you give it an still not clear if the input is an instance of the problem. Yeah, I would assume the input is an instance of the problem. Yeah, and then you run it through the circuit, and then you do that. You know, all what we've been seeing with VQE, right? So you basically you either do multiple measurements and then you do the expectation, get the expectation value of your kind of the cost function, and that's what you're trying to then maximize or minimize, and then you iterate over those angles. So basically, you're building a model, a parameterized model, and if that model is good enough, then you kind of can with whatever classical techniques find the minimum. And I think that's the idea. With that model, you're basically designing a solution space that you want to explore, and then you do those iterations and you explore that and you find the minimum. Yeah, and that's basically, it's a QAOA is VQE, really. It's just a really concrete example, and I guess VQE can be, then it's got a more of an abstract concept. You can approach it in different, use it to approach different problems, not just combinatorial problems, and QAOA is just for combinatorial problems. And it basically tells you that what you have to do is you map those constraints into your into a circuit. Yeah, but it's the same thing. Perfect. I think we can move on now. So the next video, I'll try to go back to basically the Yellow Submarine project, and try to close that gap flying over the continuous variable quantum computing. I'm not going to get into this a lot, but I want to kind of get a rough grasp of the gates and all this kind of stuff. I think it's worth knowing, and it's going to help me close that, as I said. So basically, these and these are my next targets in here. These and these. Perfect.